Morning. Um, okay, I'm just going to go through the homework and I'm going to start energy today. And then, like I said, we won't get through energy in one day. It might take 2 or 3. I don't know if I can't remember if I said it, but there's no practicals, there's no experiments in this chapter. So you have all but one mechanics experiment done now. And the last one is the higher level one, which we won't do till 6th year. So you should have 6 mechanics experiments done, and then we'll do the 7th one kind of, I think it's around Christmas of 6th year, I think. And then so the next chapter, we have I think 2 chapters of heat and 4 experiments. It's quite a bit in heat. Anyway, so the homework, this was all on work. So a husky dog does 20 kJ. Did you get that? Kilojoules. So kilojoules means we multiply it by 1,000. So it's 20,000 joules. So a husky dog does 20 kilojoules of work as he pulls a sleigh with a force of 340 newtons. Through what distance does he pull it? Okay, so our formula, change the view on this slightly. Our formula for question 3 is work equals force by displacement, or in this case distance. They don't specifically ask for a displacement in this one, but you can assume that the husky dog was pulling it through a straight line, because the formula we have for work will only give us the straight line distance. Through what distance does he pull it? So the force, now a husky dog does 20,000 joules of work, so that's actually our work. So the 20,000 goes in here. Force, as he pulls the sleigh, with a force of 340. So we have the force. And then the distance presumably is our variable. And it's the question, through what distance does he pull it? So we don't know S. Okay, we're trying to get S. At the moment it's being multiplied by the 340, so we need to divide by 340 to cancel that out. And then divide by 340 on the far side. So 20,000 divided by 340 is, I have a distance of 58.82 to 2 decimal places. And it's a distance, or displacement, some meters. Displacement is a vector, so had they have given us a direction, we'd have to put that down, but they didn't give it, so we don't need to worry about it. Okay, question 6. A man carries a 60 kilogram bag of coal up a staircase. The vertical height through which he rises is 8 meters. The man exerts an upward force on the coal equal to its weight throughout its journey. Okay, so this is where the fact that he's carrying it and holding it, he's holding it against gravity. So we're going to have to take that into account. Calculate the work done by the man on the bag of coal. Alright, so same formula. Work equals force by distance. This time it's calculate the work, so we don't know it. And the force. So they didn't give us the force, but they did give us the mass. And then they tell us that he's going to carry it. So he's going to carry it against gravity, so we're going to need to multiply the 60 by 9.8 to figure out the force or the weight. And that's 588. Okay, and that's your force. So W is W, force is now 588. And then the distance, it says the vertical height through which he carries it. And remember this, again, distance is a displacement, so it's a straight line distance. So if we're talking about carrying it in against gravity, we're talking about vertical plane. Okay, so when he picks it up and you calculate force, you're using 9.8 there. 9.8 is a vector which acts directly downwards in the vertical direction. So the displacement has to kind of match that. Okay, so again, even though he is climbing a flight of stairs, isn't he? Yeah, he climbs up a staircase, which presumably is not vertical. What we care about in order to calculate the work is the vertical height. So the vertical height is 8. And so 4704, and that is a work, so just okay. And then the last one, a man of mass 105 kilograms climbs up a ladder of length 10 meters, which is inclined at an angle of 40 degrees to the horizontal. Find the work done by the man going from the bottom to the top of the ladder at a constant speed. Neglect the effects of friction. And how much work would this man do if the ladder was vertical? Okay, so again, it is find the work done. So W equals Fs, and we're going to need to figure out our work. Okay, so we do have this man who's going up a ladder, so he is going through a vertical height. So he is going to go against gravity. So we're going to take, same again, his mass, and we're going to multiply it by 9.8. So that's 1029 newtons. Okay, and like I was saying in the last question, the S needs to match the force. So the fact that we're figuring out that this man's weight, because he is taking his body off the ground against gravity, and gravity acts in the vertical plane, we're going to need to figure out the vertical height that he travelled. Okay, so we have a ladder. I'm just going to draw it over here. We have a ladder that's 10 meters long. Okay, but that ladder is not vertical. It is inclined at an angle of 40 degrees. Okay, which makes sense. That's the way you put up a ladder. Otherwise, you'll fall. So for our S, this here, that's the ground. That's the ladder. Yeah? So what we need to know is that. So he's going to start down here. He's going to climb the ladder and he's going to finish up here. His vertical height change is between those two arrows. Does that make sense? So it's going to be trigonometry. Here's the right angle, so opposite the right angle is the hypotenuse. Here's the angle, so opposite the angle is the opposite, and that makes the ground the adjacent. Okay, when you're doing this, you always need to leave one out because all the trigonometric ratios only use 2. We don't want to leave out the hypotenuse because it has a 10 on it, so it'll be handy for us, so don't leave that out. And hopefully it's obvious we can't leave out the opposites because that's what we're trying to find. So we leave out the adjacent. So we're looking for opposite and hypotenuse. I'm going to go into my table book. What should I say? Opposite and hypotenuse. Where is it? Formula and tables. Maths. Trigonometry. This is the last page. So opposite and hypotenuse is what I'm looking for. So it's this one. Can you see it? The opposite and the hypotenuse. So it's sine. Okay, that's the one I'm going to use. Oh no, not that. Okay, so the sine of the angle is opposite over hypotenuse. It's the one I've chosen. So the sine, the angle is 40. The opposite I don't know. And the hypotenuse is 10. If I want to figure out what the opposite is, at the moment it is being divided by 10. So I need to do the opposites. And I need to multiply it by 10. The multiply 10 and the divide 10 will cancel each other out. And then I need to multiply 10 on this side. So 10 multiplied by the sine of 40. Oh, I'm in yellow. Is, again, to 2 decimal places, is 6.43, and then everything's gone except for the opposite. So I've figured out the opposite. Okay, so now I know how high he went in the vertical. He went 6.43. Now, I've written down 6.43, but in my calculator I've kept the whole number. Okay, because it's not the answer. So maybe I should write that slightly differently. So 6.427, and I'm just going to put 3 dots. I'm going to do the same thing over here. I know I don't have a lot of space. 6.427 dot dot dot. Yeah? Okay, so I'm going to keep the full answer in my calculator and I'm going to multiply it by 1029. And now I can round it. So the work done by this man is 6614.28 joules. Yeah? It asks at the end how much work would he do if the ladder was vertical. So if the ladder wasn't at that angle and it was actually vertical, then it would be the same man, so 1029, but his vertical height would be the full length of the ladder. So 10290 joules would be the work that he would do in that case. Yeah? Okay, so hopefully that went alright. That's the homework. Okay, so I just want to have a quick look at energy. So I did say at the start of yesterday's video that energy, or there was overlaps between the parts of this chapter. And there's a massive overlap between work and energy, because energy is the ability to do work. So if you have energy, you can use it to do work. Or you can think of it, if you do work, you use energy. Or lose energy, maybe is a good way to say it. Like if you think about the man going up the stairs, right? So we calculated that he did work. I can't remember what the number was, but he did work by taking himself and his bag of cement up the stairs. Okay? In order to take that bag of cement up the stairs, he had to do work. So he would have used energy in his body and he would have lost that energy in doing work. Yeah? And then work would have been done to the bag and the bag would have gained energy. It went from the bottom of the stairs to the top of the stairs. So it gained a particular type of energy as it did that. Okay, so there's this like constant transfer going on where if you're doing work, you're losing energy, and if work is being done to you, you're gaining energy. Okay, so they're very, very linked, work and energy. But by definition, energy is the ability to do work. And that's kind of the way I was talking about it there, is how you need to think about it. So when you do work, you lose energy. When work is done to you, you gain energy. I have written this. It's just off screen. Okay, so anything that can do work has energy. Yeah, and remembering again that work is exerting a force and causing an object to move through a distance. So anything that's capable of doing that, anything that's capable of exerting a force and moving an object through a distance has energy. Yeah? So there's all different types of energy, and we'll pretty much come across all of them, but some of them we do a lot more kind of calculations and questions with. So the two that we're going to use the most in this chapter are the first two there, kinetic energy and potential energy. So kinetic energy is the energy an object has due to its movement or its motion. So as soon as something is moving, it has kinetic energy. Yeah, no, it will have got it from somewhere, because we'll talk about this in a minute, but energy is never created or destroyed. So if something gains energy, it got it from somewhere. If something loses energy, that energy's gone somewhere. Okay, so it's never a case that, like, when I get up, say me now, say I get up away from this table and I walk, I have moved, so I have kinetic energy. Where did that kinetic energy come from? It came from the chemical energy inside me because I ate my breakfast. So the food went in my body without getting to biology, but respiration occurred, and that gave me the energy to walk across the room. Okay, so energy, if you have gained a certain amount of energy, like me moving across the room has given me, I now have kinetic energy that I don't have when I'm sitting here. The energy to walk across the room has come from somewhere. Okay, it's always transferred. Second one then, which we're going to do a lot of in this chapter, is potential energy. So the potential energy is the energy a body has due to its position in a force field. Now we'll talk about this later in the chapter, but there's different types of potential energy. In this chapter a lot we talk about gravitational. So see the way it says in a force field? It can be in different force fields. It just depends what's exerting the force. So potential energy can be due to your position within the gravitational force field, which essentially means that when something is higher, it has more potential energy than when it's lower, because it has more potential to fall. As in, if something, I don't know, if something fell off a table versus falling off a roof, by the time that something hits the ground, it's going to be traveling much, much faster. It's got much more capability or potential to pick up kinetic energy and get faster and faster and faster and faster. Okay, so the higher something is, the more potential energy it has, and that is due to its position in the gravitational force field. So if it's higher, it has more potential than if it's lower. Now you can also have what's called stress potential energy, and there's electrical potential energy. So there's lots of different types of potential energy, just depending on what force field you put it in. Okay, but the one we're going to talk about most in this chapter is going to be the gravitational potential energy. Okay, just due to its position in the gravitational force fields. So the higher you are, the more potential energy you have. Electromagnetic energy. So we're going to talk about the electromagnetic spectrum at the end of the light chapter, I think. But this is energy that is transmitted from one point to another in the form of electromagnetic waves. They travel really fast, they travel at the speed of light, and there's all different types: radio waves, microwaves, heat. Heat kind of gets its own little brand as well, internal energy or heat energy. So again, there's no point in talking about this here because we are going to do heat. It's the next chapter we do, so we will talk about heat energy and what happens when you add heat to a system, what happens when you remove heat from the system. Okay, so we will go through that in a lot of detail. Sound energy, again, there is a whole topic on sound, so we will talk about sound as a form of energy, but essentially sound is just a vibration that then propagates through the air. Okay, so, and again, it has the ability to do work, it has the ability to exert a force and cause an object to move through a distance, so it's a type of energy. Chemical energy, so that's energy that is given out or sometimes taken in the form of heat, light, or kinetic energy during a chemical reaction. So I was just talking about when you eat, it is a chemical reaction that takes place in order for you to be able to use the energy that you take into your body to turn it into, in my example, it was kinetic energy. Chemical energy is like probably one of the only ones we don't talk about a whole lot because it is much more based in chemical reactions, and obviously if you talk from respiration, it's more based in biology, so there isn't a section in physics on chemical energy. Electrical energy there is, so we do circuits and we talk about electrical potential energy. So basically, as an electron moves through a circuit, what forces are acting on it and what type of energy is it gaining, what type of energy is it losing. So we talk about that in great detail. And then nuclear energy, so energy produced from fusion and fission reactions, and again that is a whole topic. So all of these different types of energy we will come back to, probably except chemical, and we'll kind of learn about them in a lot more detail. But for now, so the conservation of energy, this is really important. I just spoke about it a second ago, but you need to know this. So the principle of conservation of energy states that energy cannot be created or destroyed, but can only be converted from one form to another. So like I said, when you see, I don't know, a light, we know that light is a type of energy, but it came from somewhere. So something has happened in order for you to be able to see that light that has come from somewhere. So for most people, it's because you flicked a light switch, which means there's electrical energy. And then the electrical energy for most people comes from your mains. It's, just in your house. But that energy has to be generated from somewhere. So again, you take it back to, our massive energy crisis. Like, so where does that energy come from? Is it from gas? Is it from the burning of fossil fuels? Is it like hydroelectric? Is it, where was it that the energy came from? So you would have done, I know I did these with my third years last year, and I'm doing them with my third years actually as soon as I come back. You would have done some of these conversions. So I don't know if you remember them, but you can demonstrate the conversion of energy. Like, you can use a solar panel, like a little mini solar panel, and attach it to a motor, for example, and shine light onto the solar panel. And you can see then the motor, it normally has like a little windmill on top. And when you shine light onto the solar panel, your light energy is being converted into electrical energy by the solar panel. It travels through the wires, and then once it reaches the motor, it is transferred into kinetic energy because the motor is moving. So you can see that conversion. So they've like different types of conversion here. But yeah, I suppose it's just to understand that the energy is always being transferred. So when there is a demonstration of a type of energy, generally you can see, or you should be able to kind of trace where it came from. A lot of the time in interactions of, like even that example I just gave there, where you have a solar panel, you shine light on the solar panel. The solar panel is designed to turn light energy into electrical energy, so it does that. But nothing is 100% efficient. So a lot of the time in energy transfers, you have wasted energy. So like if you have so this is our solar panel, and we use like a torch or something, and we shine some light energy onto the solar panel. And then the solar panel is like in a circuit. Then let's say in here, I'm just going to make it a circle. This is like your little windmill thing. And I'm just going to connect it all up, just so it makes sense. So the light energy shines on the solar panel. The solar panel is designed to turn or transfer the light into electrical energy. The electrical energy will then go through the wires, and then once it gets to here, the electrical energy is turned into kinetic, and the windmill will spin. Okay, but during these like transfers, when the light energy is turned into electrical and when the electrical is turned into kinetic, it is never 100% efficient. So what you get, like in this, you get like heat given off, which wasn't necessarily designed, as in it doesn't go anywhere, it just kind of dissipates into the air, and the air around the solar panel will get a little bit hotter. If you touch the solar panel, you'll feel that it's a little bit hot, and not necessarily in the area where you were shining the torch. And so that's wasted energy, and that will happen depending on the device. Like obviously the better devices will be more efficient, so they won't waste as much. And there'll also be loss here. If you've ever heard this little thing working, it makes like a little like, there's a little like whirring sound, and that sound energy that doesn't actually contribute to turning the turbine. It's just that it happens to make a sound, and that's wasted energy. And again, if you leave it on long enough, it will get hot as well. So that's heat energy. Generally speaking, the wasteful forms of energy are sound and heat. And so yeah, you'll never get a system that's 100% efficient. So when those transfers take place, there is energy always being transferred into wasted energy. So it kind of the amount of energy available is sort of dissipating. Yeah, so that's the principle of conservation of energy. Now, what I wanted to talk about today was kinetic energy. So this is moving energy a body has due to its movement, and it can be calculated. So kinetic energy, EK, is a half mv squared. Now, as always, this is in the table book. So the EK, the E is obviously energy, and then K makes it kinetic energy. The M is mass, and the V is velocity. Yeah. So a body of mass 1,000 kilograms is moving with a velocity of 40 meters per second. Calculate its kinetic energy. So kinetic energy is a half mv squared. Calculate the kinetic energy, which means we don't know it, so I'm just going to write it in. The half is a half, which is fine. M is mass, and mass is measured in kilograms, so that's that. And then V is velocity, and there's your velocity. It's in meters per second, which is the correct unit. So we go 40, and just don't forget to square it. So that is, if I did that right, is a kinetic energy of 800,000. Now, I don't know if I talked about this at the start, but because energy and work are interchangeable, as in when an object has energy, that object does work, or when an object does work, it loses energy. So because they're completely interchangeable, their units are the same. So energy is measured in joules as well. Yeah, just checking my calculation was right. Yeah. And then we'll have a look at this one. So a man of 30 kilos has a kinetic energy. Man of 30 kilos, wow. Has a kinetic energy of 1,000 joules. Find, a mass. Okay, that was a pretty small man. A mass of 30 kilos has a kinetic energy of 1,000 joules. Find its speed. Okay, so kinetic energy is half mv squared. So starting with kinetic energy, we're given the kinetic energy. So the 1,000 goes in there. The half is just a half. The mass is 30, so that's going to go in there. And then find its speed means we don't know this. So that's v squared. Okay, so we are trying to figure out what v is. So I suppose we'll do any multiplication we can, which we can multiply a half by 30. So we'll do that. So that's 15 v squared. Again, we're trying to isolate the v squared, so we can get rid of the 15 by dividing by 15 and then mirror that on the other side. So that gives us 66.6 recurring equals v squared. We don't want v squared, we just want v. So to get rid of the squared, we do a square root, but again, we have to mirror that. So the velocity or the speed is 8.16 meters per second is the speed of this mass. Okay, so there's a couple more questions there which we will do tomorrow, but let's get you to have a go at a few of these. Okay, so we'll do question 3 and question 4. I'm just going to see if there's another one then. Tuesday the 11th. So question 3 and question 4. No, maybe not yet. Yeah, we'll do 5. So 3, 4, 5. Right. Okay, so that is your homework. I'll correct that tomorrow.